you guys should probably be able to see this. So if I'm being entirely honest, we're going to wrap this up pretty quickly because I spent 4 hours making 3.5 pages of notes because that's how much this stuff confuses me. So we're going to get through what we can get through, and that'll be that.
That's scary.
No. Nope. So when is this thing going to show up? All right. So up here
Oh.
in front of us is a DC machine. I'm going to talk about things and then I'm going to vastly simplify it so we can understand how it works. Okay. This is an extraordinarily complicated piece of machinery, much more so than an induction motor or a synchronous generator, or excuse me, a synchronous machine. So I'm going to talk our way through things. So let's start. It is a rotating electrical machine. So it has a stator, which is stationary, and an armature or rotor, which turns. So luckily for us, it has that in common with the machines that we've dealt with. Okay. So let me put the screen down here so I can draw on things as we talk about stuff. Let me get a nice color going here. So no, do not. No, do not draw this. Very much do not draw it. I'm just going to talk about the different parts because as we talk about the different resistances and all that kind of stuff, they're going to come from this drawing. Okay. So our stator is what carries our excitation field, right? So we have this thing right here labeled as our main pole core. So this is a 2-pole machine. There's a single north pole and a single south pole. And around these pole cores are wrapped our field windings. There are 2 different field windings because we can connect a DC motor in 2 different ways. We have our shunt field windings that are here internal on both sides. Okay. And so our shunt field winding is a whole bunch of turns of very thin wire. Okay. And we use this connection when we're connecting in parallel. And then wrapped around the outside of our shunt field winding is our series field winding here and here, and it cylindrically wraps around those pole core physical pieces. And so this series field winding is another coil, but it is made of very thick wire and it only uses a few turns. Okay. So we do that so that the resistance is very small because the larger the wire is and the less number of turns we have a very low resistance. Our shunt field winding uses very thin wire with a whole bunch of turns so that it has a very high resistance and looks like effectively an open circuit when connected in parallel. Okay. So we have these 2 different types of field windings that we can use for 2 different connections. And they are separated by a thin insulating layer. It is literally usually paper. So just enameled wire so that it can't short anything out, wrapped around these main pole cores. Okay. These windings are wrapped around what's called the D axis or the direct axis. Okay. So the direct axis is the axis of symmetry that flux travels through. So when flux travels around this motor structure, it's going to do something like this. It's going to go around this path and go around this way. And there's going to be a similar flux path around this way. So that D axis is literally just the direct axis, which is the axis of symmetry for the different flux paths that are taken when the motor is in operation. Okay. We also have compensation windings here. Okay. So effectively, we are going to have some current flowing through our armature windings, which we haven't talked about yet. And that current is going to cause a distortion of the stator field. And so we use the compensation windings to make to correct that distortion, so that our motor operates at its best possible operating point. The compensation windings only really occur in very large motors. So in smaller motors, we don't really care about it, but in really large motors that we're trying to operate at a relatively high efficiency, we need to have those compensation windings. It is expensive to put them in, which is why they're only in big, expensive machines. Okay. So let's see, that's pretty much everything that is attached to our stator except our commutating poles, and we'll talk about those once we talk about commutation here in a moment. So if we move along, one thing that I hope is super obvious, this thing I'm highlighting in green right here is an air gap. So we are passing flux across an air gap like we have in every other piece of rotating machinery that we're being dealt with. So our central thing here is our armature or rotor. And so we have an armature winding forming loops, much like we had for a squirrel cage system, for an induction motor, or in our synchronous machines, okay? Then we have our brushes. So these black boxes here and here are brushes that are made of carbon filaments, and they are used to conduct electricity to what's called the commutator. So that's how we apply a voltage or how we get voltage off if we're using this thing as a generator. Our brushes are stationary and they're brushes so that they slide while remaining in contact as our rotor and everything turns. That brings us to our commutator. So the commutator is that ring in the middle that's cut up into a bunch of little bitty sections, okay? The role of the commutator is to change the direction of the current that is flowing through the armature windings. And we'll talk a little bit more about that when I look at a simplified version of this machine here. So because we're constantly changing the direction of the current, very often we will see sparks and stuff like that fly off the trailing edge of our brushes because of electromagnetic induction, right? We have, since we're changing the direction of the current, the flux changes directions instantaneously, inducing a large voltage. We have a large voltage, it causes sparks to cause things to catch back up effectively. To limit the amount of sparks and stuff like that that we're going to happen, because they tend to actually damage the machine over time as well as literally burn up the brushes, we have those commutating poles. The commutating poles and the brushes are aligned along the Q axis or the quadrature axis, which is 90 degrees out of phase. So effectively, it's a neutral axis. And what those compensation poles do, or excuse me, the commutating poles do, is they induce a voltage in the commutator section that is performing commutation. And those voltages effectively cancel each other out so that you don't get nearly as many sparks by the changing current, okay? So that is effectively all of the different important parts of a DC machine. So once again, this thing is annoyingly complicated because it relies on some interesting principles. So let's break this down into something way more easy to understand. Scroll back to the top here. So let's say that I have a structure like this, okay? So this thing right here is representing one of my, let me use the right term. That's the wrong page. We'll talk about that diagram in a moment. main pole cores. So this is representing one of my main pole cores. Let's, for the sake of argument, call this the North Pole, and we're going to have some winding wrapped around it. So this is going to be our field current. And I'll terminate this winding in a couple of minutes. Down here on the bottom, we have the other part of our main pole core. I drew that too big. So this would be our south pole, and our winding here is going to come across. And wrap around like so, and then here's the return path for our field current. Across the terminals of our field winding, we apply some field voltage, and we're going to have some magnetic flux that is generated by that field winding, which is called phi D, because it is the flux along the direct axis, or the flux along the D axis. Okay, so this thing right here effectively represents what's going on with our stator. Okay, so now let's simplify our rotor by a ridiculous amount, by instead of saying that we have a whole bunch of coils wrapped around this rotating thing, we have a loop of wire. So I'm going to try to draw this as best I can in a 3D space. I'm going to draw this wire in red. So we have this rectangular loop that is capable of spinning inside of this area. And how am I going to draw this? These little half circles here that I'm trying to draw represent our commutator. Okay. This black thing here is our brush. Here are the terminals on the armature side. So I'm going to call this VT for my terminal voltage. This current is IA for my armature current. And then if I want to have some actual armature current flowing, I need to connect some kind of load resistance to this thing. Okay. So I have a loop of wire that is rotating in the presence of a constant magnetic field. What's going to happen? I have a single loop of wire that is rotating in the presence of an external magnetic field. Current and voltages will be induced. Absolutely. Just like we've seen in literally every other thing. Well, let me choose this direction for the sake of argument. So we are going to have some EMF EA and some current IA induced in our wire as the area that the flux passes through changes, right? So as that square loop rotates around, it sees a varying flux. When it is horizontal like this, it sees the maximum amount of flux. As it turns, it sees less and less flux, which causes a change in the voltage. So if we were to look at a simple system where we were using slip rings, effectively our induced voltage would look something like this. So this is EA, our induced voltage as a function of time. And let me do it in blue just for the sake of argument. So this is the behavior that we would get if we were using slip rings like a synchronous generator. Okay. But we're not using slip rings. We're using a commutator and brushes. Okay. So what that commutator and brush system do is they provide rectification. So what does rectification mean? You guys have had classes involving electrical things. Anybody know what rectification is? Turning it towards DC. Absolutely right, Hugh. So with our commutator in place, what we see in our DC, it's called a generator in this case, is effectively the same thing, but all of our negative half cycles get turned into positive half cycles. Okay. So let's talk about why that is. So when our device spins around, effectively the vector area of that loop is pointing out. Let's say that it's pointing out in the up direction or whatever. And as it's turning and turning and turning, the vector area turns along with it until we hit that commutator, which changes the direction of the current. And so our area rotates in the opposite direction. And then it just goes back and forth, back and forth. So our vector area is effectively always up, which means our induced voltage is always going to be positive. Okay. So what if we had more than one loop and our commutator was divided into more than two sections, right? Because two pieces of commutator for each loop that we have. Well, if I superimpose a bunch of more loops on here, so this is what happens when we add multiple loops in, we're going to have lots of this rectification going for lots of voltages. So let's put another one kind of out of phase like so, and maybe another one here. And what happens is we start to see a voltage that's always positive, but has some ripple on top. The more loops we add and the more we subdivide our commutator, the smaller that ripple is until we are effectively outputting a DC signal. So this is a very, very simplified version of a DC generator. We spin our armature mechanically in the presence of some external magnetic field supplied by an electromagnet. And with the commutator system in place, we wind up getting a DC voltage, or really a constant voltage with some AC ripple on top of it that we can make look like a DC voltage if we put enough turns in there. So that's the operational principle of a DC motor. Okay. All right, so let's talk about, let's not use that bright red color there. Our induced armature voltage. So our induced armature voltage, EA, is given by the equation Z, and I'll talk about what this means in a moment, times P over 2 pi A times our flux times the speed at which we spin our rotor. So Z is the total number of conductors. This is twice the number of coils times the number of turns in each coil. We'll talk about that in a moment. P is the number of poles that our system has. 2 pi is just 2 pi. A is the number of parallel paths that our armature current takes. Phi D is the direct axis flux per pole. And omega M is the angular velocity of the shaft. Okay. All right, so I'm going to tab over to something that you guys don't have to draw this thing either. I'm just trying to explain what some of these things mean. So our textbook does a pretty terrible job of it. So I found another one. Let me scroll up here. So the Z is related to the number of conductors in the winding. And so this diagram right here is effectively trying to explain the difference between a turn, a coil, and a winding. So a turn is what we expect. A single turn, if we have multiple turns wrapped together, we get a coil. And if we string multiple coils together in series, we get a winding. So Z is just twice the number of turns times twice the number of coils, which is the total number of conductors in the winding. Okay. That quantity A, the number of parallel paths, has to do with how that winding is established. So this thing right here, this ugly, horrifying looking thing is what's called a lap winding. I do not expect you guys to understand this because honestly, I don't fully understand it. And I've watched like 4 YouTube videos trying to explain it to me. But effectively, it's called a lap winding because as you wind up wrapping these coils into these slots, they overlap each other as you go around the armature or rotor here. So for a lap winding, a simplified representation would look something like this, where these pluses and minuses are corresponding to the positive polarity terminals and negative polarity terminals of our brushes. So for a lap winding, we wind up having 4 different parallel paths that our coil currents can take to form our armature current. I do not want to upgrade my computer to Windows 11. I wish it would leave me the hell alone. So for a lap winding, we're always going to have A is equal to 4. The other option that is very commonly used is what's called a wave winding, because it looks like a wave as we wind it through the different slots. And a wave winding results in 2 parallel paths. So effectively, based on the relationship that we have here, a wave winding is going to give us twice the voltage as a lap winding because A is in the denominator of our fraction. Okay, so 2 for wave winding, 4 for lap windings. This term here, Z times P over 2 pi A, is very often written as Ka, which is the armature constant. And it effectively represents a coefficient that represents how the armature was constructed, total number of conductors, whether it's a lap winding or a wave winding, etc. Okay. So we could also say that our induced voltage EA is simply Ka times our flux times the speed at which our shaft is rotating. Okay. So let's work a mathematical example here, just real quick, to illustrate what I mentioned a moment ago. Our induced voltage in a wave winding should be twice as much as our induced voltage in a lap winding. So let's say that the armature of a 4-pole DC machine is operating or rotating at a speed of Nm is equal to 1800 RPM. The armature winding consists of 33 coils with each coil containing 5 turns. If the flux per pole is phi d is equal to 50 milliwebers, I want us to determine our induced voltage EA if the armature is lap wound, and B, the induced voltage EA if the armature is wave wound. Okay. So Z, the number of conductors, this is going to be constant for both situations, right? So we have twice the number of turns times the number of coils. So this is 2 times 33 times 5, comes out to be 330 conductors. P, our number of poles, is simply 4 from our problem statement. A, the number of parallel paths is also 4 because we have a lap winding. And so from this, our armature constant Ka is Z times P over 2 pi A. So that looks like 330 times 4 over 2 pi times 4, which comes out to be 52.521. And this is a unitless quantity. Our induced voltage, EA, is simply Ka times our flux per pole times our rotational angular velocity. So that's going to be 52.521, excuse me, times our flux, 50 times 10 to the minus 3. So that's me getting rid of the milli. A Weber is a volt second. So I'm just going to express this as volt seconds so we can see where that's going. And then I have 1800 revolutions per minute, RPM, multiplied by my conversion factor of 2 pi over 60 to put it in radians per second. So the per seconds cancels the seconds, and we just wind up with volts if we're looking at this thing from a unit perspective. And we get an induced voltage of 495 volts. For part B, Z is the exact same thing. P is still 4. A in this case is 2. And so our armature constant, ZP over 2 pi A, looks like 330 times 4 over 2 pi times 2, which is literally just twice what we had earlier, or 105.042. EA is Ka times phi d times omega m, 105.042 times that same 50 times 10 to the minus 3 volt seconds times that same 1800 RPM times 2 pi over 60 gives us 900. Must have written that down wrong. 990 volts. Let's throw this in the account. Jules, what are you getting for things? Did I make a mistake in the first part or the second part? Should it be 445 or 495?
Yeah, the same thing.
Even with the
I took.
yeah. Let's see here, just real quick. 330 times 4 over 2 pi times 4. $52.521 multiply by 50 times 10 to the minus 3 times 1800 times 2 pi over 60, 495. Okay, that checks out. 330 times 4 over 2 pi times 2, 105.04, blah, blah, blah. That multiplied by 50 times 10 to the minus 3 times 1800 times 2 pi over 60, 990. Oh, 990 is 495 times 2. That's just me not being able to do math in my head. Okay, sorry about that. I was like, no, 990 should be 445 twice, but nope, that would be 890. I'm just bad at math today. My apologies for wasting your time. All right, so it's that kind of day. All right, so simple calculation regarding calculating the induced voltage if we know our rotational speed and we know our flux and all that kind of good stuff. All right. So, yes, ma'am. Yes. Yes. So wave wound is, there's half as many parallel paths as lap wound, right? So let me. Because the number of parallel paths is in the denominator. Dividing by. Yeah.
Okay.
Yeah. All right, so now let's look at an equivalent circuit for this thing. So I'm saying equivalent circuits because we're going to have a situation very much like we had with our synchronous machines, where we're going to have one equivalent circuit for generator operation and one equivalent circuit for motor operation. And the only difference between those equivalent circuits is the direction of our armature current, which is exactly what we saw in our synchronous machine as well. Okay. So for a generator, we're going to have this equivalent circuit where this resistance represents the resistance of our field windings. So we apply our field voltage VF across our field windings, generating some field current IF that causes our flux phi D, right? So this is the representation of our stator circuit. Our armature circuit, I'm going to put over here. I'm putting these terminals A1 here and A2 down here, and I'll explain that is in a moment. So here we have some resistance RA, and then down here we have our induced voltage EA. And then these are the terminals on the armature side. So I'm going to call this voltage VT. And when I'm dealing with a generator, this is the direction of my current IA. So I've labeled those armature terminals A1 and A2 separately because those are the terminals where we can actually apply things to the armature. So very often in some textbooks and stuff like that, they won't even represent the armature resistance at all. It's usually very, very small, on the order of tens of milliohms. So it's not a whole heck of a lot to deal with. They usually just lump it in or effectively neglect it and only have that induced voltage, but I wanted to make it explicit there because we are going to keep it in for the sake of simplicity and understanding what the hell is going on. Okay. So this is our generator equivalent circuit. Our motor equivalent circuit is literally the exact same thing, except the direction of the current IA is the other way around. So here is RF, VF, IF, showing my armature terminals A1 and A2. We have our resistance RA. Our induced voltage EA. And then our current IA will be flowing in the opposite direction. Here is our terminal voltage VT. And so this is what we have when operating as a motor. So on the armature circuit side of things, we can develop a simple relationship using, Kirchhoff's voltage law that says EA, our induced voltage, will be equal to VT, our terminal voltage, plus or minus, we'll talk about this in a moment, IA times RA, where the plus here is when we're operating as, let me look at this thing, a generator. And the minus here is when we're operating the motor. So if our terminal voltage is larger than our induced voltage, what do we have? A motor. If our terminal voltage is less than our induced voltage, we're operating as a generator. Okay, the last thing that I want to talk about for today is a simple relationship here. So we are looking effectively at our air gap voltage here, much like we did in our synchronous machine, right? So this is the induced voltage that's caused by our flux crossing our air gap. So this is where our electromechanical energy conversion is occurring. So if we are working with a generator, this is the output voltage in an open circuit system caused by us spinning our rotor, or if we're operating in a motor system, we're looking at effectively the output power delivered directly to our shaft caused by induction, right? So at this point in our system where we're looking at purely the developed torque or developed mechanical power or developed electric power, those two quantities have to be equal, and then we'll have losses that we'll deal with in a little bit. So from that relationship that we know that the mechanical power developed has to be equal to the electrical power developed, we can say that P, let me do this in black. I'll do it down here actually. So PD mechanical is equal to PD electrical. Our developed mechanical power is our developed torque multiplied by the angular speed at which our rotor is turning. And this is equal to our induced voltage times our armature current. Our induced voltage is Ka times our flux phi d times omega m times Ia. And so we can see that the omega m's on both sides here cancel out. And so our developed torque Td is equal to Ka times phi d times Ia. So the more current we drive through our DC motor, the more torque we get. And then we'll go into speed torque relationships and all that kind of good stuff with our next class meeting. All right, I've made you guys suffer enough, and also I didn't prepare anything else. So have a good rest of your day. Actually, let's talk briefly about your final in this class. So you have one more exam remaining, and it is going to be on DC machines. That's it. Okay. Much like what we saw with the last exam, I would expect this exam to be very, very similar to any homework assignments I give you, which will probably just be one homework assignment that I'll put up after class on Thursday. And the example problems that I'm working in class so that you guys have some idea of what to use to study and all that kind of good stuff. So I sincerely hope to finish up everything that I want to talk about, which I honestly don't know what that is at this point, regarding DC motors for class on Thursday. And then Monday, Tuesday, and Wednesday of next week, we are out for the Mardi Gras break, which leaves 2 possible class meetings for your final. Thursday, the 23rd of February, or Tuesday, the 28th of February. So I am open to suggestions, but I am leaning towards having you guys take your final on the 23rd of February. The largest reason there, and I was discussing this with Jules earlier, is that if I give you guys the exam on that Thursday, that means that there's time for my graders to grade your exam, and they're much less of jerks than I am. I hate grading with a passion, so I'm usually in quite a bad mood when I do it, and scores tend to be not super great. So my preference would be for you guys to do it on Thursday. But I also understand that some of you may be traveling. Some of you may be recovering from an amazingly huge hangover and things like that. So what I'm going to do, I believe, is actually just give you guys the option. I'll be here both days and you can come take your test whatever day works for you. How does that sound? All right. So be aware, though, that if I'm grading, if you show up on that Thursday, there's a very high possibility that the asshole sitting in front of you is the one grading your test, just to be clear. So I cannot encourage you enough to take it on Thursday, but if you want to gamble, come take it on Tuesday. All right, see you guys later.